Hello everyone, this is Weber from Algorency. Now today's topic is complexity analysis. You know guys, complexities are the backbone, or we can say fundamentals, behind the implementation of data structures and algorithms. As we know guys, every problem in this world has different or multiple solutions. Some solutions are a bit better than others, but in some cases they create a difference in greater extent. While we face a coding interview, the first question our interviewer gonna ask us, after we present our answer, that can you improve your answer or can you do better? By this question, he is obviously not referring about your handwriting or anything else. All he wants from you is to reduce the space-time complexity of your algorithm. In computer sciences, complexities are further divided into two parts: the time complexity and space complexity. Time complexity means the time taken by algorithm while execution or for execution, and space complexity means the space uses up by your algorithm. Together we can call it space-time complexity. The time and space complexities of an algorithm are not particularly fixed. They change according to the size of input. So how can we generalize the space-time complexity? Or we can say, on what scale shall we measure it? So here comes the use of big O notation. In this way, we can represent the big O notation. A capital O, then under the parenthesis, a function. The function which is directly related to the input size. Listen carefully, a function which is directly related to the input size. Here, a function n, that is n, relate to the size of inputs. Okay. So big O notation allows us to generalize the complexities of an algorithm as a function of its input size. So first complexity is time complexity. Okay. So I'm gonna explain you this with the help of example, guys. Okay. So first I will give you a practical example and then with the help of a data structure. Okay. So assume n number of bricks and each brick is assigned with a particular number. Now here comes a boy Luffy. So Luffy's task is to find the brick with number k. Okay. And our task is to arrange those bricks in a manner such that it will take Luffy the minimal time to find the kth number brick. Okay. So the very first thing or the very first arrangement we can do is linear arrangement. Linear arrangement means we will arrange the bricks side by side. Okay. Don't focus on the order, guys. The order can be different. I have arranged them consecutively just to make it simple to understand. Okay. So here if Luffy wants to find a brick with number 3, that is if k is 3, then he is gonna take 3 units of time. Similarly, when he wants to find number 7, it will take 7 units of time. So one way we can generalize it is that if Luffy wants to find n numbered brick, it will take n units of time, as in general. So we can represent it as order of n, that is big O of n. Now coming to our second arrangement, okay, that is known as binary arrangement. Here we have arranged the brick in such a manner that the number lesser than the node will added to its left side and the number greater than the node added to its right side. Okay, that is 6 is greater than 4, so we have added 6 to its right side and 2 to its left side. Okay. Now again, here Luffy wants to find the brick with number 3. Okay, so what will Luffy do? Luffy will go to the node, then he will search that whether 3 is greater than 4 or lesser than 4. If 3 would be greater than 4, he would have gone for the right side. But since we know that 3 is lesser than 4, then he will go for the right side. For the left side, I'm sorry. Okay, so he will go from 4 to 2 since it is left side. Then he will again compare 3 with 2. 3 is lesser than or greater than 2. Since 3 is greater than 2, then he will go for the right side. And here he will find his brick. Similarly, when he wants to find the brick with number 7, You will first compare 7 with the root node 4. Since we know that the 7 is greater than 4, then he will go for the right side. Then again he will compare 7 with 6. We also know that 7 is also greater than 6. Then we will again go for the right side, and here we will find a break. Okay. Here we can see that time complexity for both numbers are same, as well as both are taking h unit of time, where h is the height of a binary arrangement. Also in binary arrangement, the height is equals to log of n, where n is the size of input. So here we can clearly see that how different approaches of solving algorithm result in different time complexities. Okay, let me take an array, guys, and name it as a, okay, of size n. Now we'll perform an operation like find a of 0. Okay, that means the value at index 0. As we know, guys, the value at index 0 is always gonna be same. Therefore, the operation gets performed in order of 1. That is, it is an operation which will always take a unit time, no matter what the size of input is, constant time complexity. Now coming to our second operation, guys. In this operation, we are trying to find the sum of whole array, like the sum of each element of array. Now for doing so, we have to iterate every element of array and add them up to a variable. Okay, something like here we have done like for I in range n, s plus equal to I. That is, we are adding up the value of each element of array to the variable s. Okay, now for doing so, it is gonna take n unit of time. Okay, now it is known as linear time complexity, that is order of n. Now third example, guys, the sum of pairs. Sum of pair means like this, like assume an array with elements 1, 2 and 3. Then the pairs will be 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. Okay, and that means if we have a size of array 3, then the number of pairs is 9, that is 3 cross 3. Okay, so that means for doing so, we have to use 2 for loops. I will say it again, that for doing or to find the sum of each pair of an array, we have to iterate it twice. Okay, by using 2 for loops. For I in range n, for j in range n, sum of I and j. Okay, this is not a mistake, guys. Actually, I have prepared this presentation on Google Slides and presenting it to you on MS PowerPoint. Okay, so it is sort of bug. So I hope you understand that this for loop is inside another for loop. This j for loop. Okay, these are nested for loops. So since we are iterating it twice, or we are using 2 for loops, that's why our time complexity is gonna be order of n square. That is n cross n. So in the same manner, guys, if we use another for loop, right, our time complexity is gonna be order of n cube. That is big O of n cube, n cross n cross n. Also in some cases, the time complexity looks like this, like order of n square plus n plus 1. Since we know that we use big O notation in order to generalize our complexities, or in order to generalize our complexity representation, so here also we will generalize it as follows. We will, as we know, n square is greater than n, and also n square is greater than 1. So in general, we can write it as order of n square. So here are some other examples of time complexities. The first one is order of log n. The order of log n, as we have seen in binary arrangement, the height of binary arrangement is equals to log of n. Okay, where n is the size of input. So it comes between constant time complexity and linear time complexity. Okay, the other one is n log n, which comes between linear time complexity and order of n square. The third one is 2 to the power n, like order of 2 to the power n. It is quite big time complexity, but the other one is simply the largest one, I think. order of n factorial. You can see guys, n cross n minus 1 up to 1, you know. So we will almost prevent using this in future. So that's it for this video guys. In my next video I'll discuss about space complexities. So thank you for watching my video guys. If you like it, do like, share and subscribe. Stay tuned to our channel guys. Um, Stay safe, stay home and keep coding. Bye bye.